The cardiac cycle includes all the events in the heart that occur with a single heartbeat. Electrical depolarization is coupled to mechanical contractions that work to pump blood. These electrical depolarizations, or action potentials, are what initiate each contraction. Contraction of cardiac muscle causes increased pressure inside each of the heart's chambers, and these increases in pressure cause the heart valves to open and ultimately lead to the ejection of blood. When thinking about the cardiac cycle, it's important to consider that blood always flows from a region of high pressure to a region of low pressure. Next, the heart valves that separate the chambers are one-way valves, so they only open when there's an increase in pressure on one side of the valve. For example, the mitral valve that separates the left atrium from the left ventricle only opens when the pressure in the left atrium exceeds the pressure in the left ventricle, allowing ventricular filling to occur. And finally, the events that occur in the left heart are the same as the events that occur in the right heart, although the left side is a much higher pressure system, and as we'll see, there's slightly different timing between the left and right sides. Now let's look at how changes in pressure lead to opening and closing of heart valves and ultimately to the flow of blood. We'll start here with the left atrium, and as long as the pressure in the left atrium is higher than the pressure in the left ventricle, the mitral valve remains open, allowing blood to flow down its pressure gradient from the left atrium into the left ventricle, causing ventricular filling. Once the depolarization signal reaches the ventricles, the left ventricle starts to contract. As soon as the pressure is greater in the left ventricle than it is in the left atrium, the mitral valve will shut. During this period, the pressure in the left ventricle will continue to rise as long as the heart is contracting. During this time, the pressure in the aorta is greater than the pressure in the left ventricle, so the aortic valve remains shut. But as the left ventricle continues to contract, the pressure in the left ventricle eventually exceeds the pressure in the aorta, causing the aortic valve to open. Blood can then flow down its pressure gradient from the left ventricle into the aorta and out into the systemic circulation. The pressures throughout the cardiac cycle are dynamic. These pressures are highest during systole, or ventricular contraction and ejection, and they're lowest during diastole, or ventricular relaxation and filling. This diagram of the heart shows some average pressures found during both systole, this top number, and diastole, this bottom number, with pressure ranges indicated by these arrows off to the side. Let's start with the high pressure system of the left heart. The left atrium contains only one number, which represents the average pressure for both systole and diastole. This is because there are only small fluctuations in atrial pressure during the cardiac cycle. So on average, the pressure is about 5 millimeters of mercury in the left atrium, with a range of about 1 to 10 millimeters of mercury. The left ventricle, on the other hand, can reach pressures as high as 120 millimeters of mercury upon contraction during systole, with a range of 100 to 140 millimeters of mercury, and they fall to around 4 millimeters of mercury upon relaxation during diastole, with a range of 3 to 12 millimeters of mercury. The left ventricle pumps blood into the aorta, where pressures are around 120 millimeters of mercury during systole and 80 millimeters of mercury during diastole. This is the typical arterial blood pressure, and these are the numbers you get when measuring blood pressure with an arm cuff. The right heart is a much lower pressure system. The average pressure in the right atrium during systole and diastole is 3 millimeters of mercury. Then in the right ventricle, the highest pressure reached during systole is 25 millimeters of mercury, and the lowest pressures during diastole are around 2 millimeters of mercury. The right ventricle then pumps into the pulmonary artery, where systolic pressures reach 25 on average, and diastolic pressures fall to about 9. All these pressures are much lower when compared to the corresponding region of the left heart. When looking at the steps of the cardiac cycle, these steps include atrial systole, where the atrium is contracting, pushing blood into the ventricle; isovolumetric contraction, where the ventricle is contracting against closed valves; ejection, where the aortic valve is open, allowing ejection of blood into the aorta out into the systemic circulation; isovolumetric relaxation, where the ventricle is relaxing with closed valves; And finally, ventricular filling, where the mitral valve opens, allowing filling of the ventricle from the atrium to occur. And then we're back around to atrial systole. Now we can look more closely at each of these events as they occur in the left heart during the cardiac cycle. Our arbitrary starting point will be during diastole, when both the atrium and the ventricle are relaxed. We're just looking at the events of the left heart, but keep in mind that the sequence of events in the right heart is the same. The main difference is that the left heart has much higher pressures than the right heart, and as we'll see later, there's slightly different timing. At this point in ventricular filling, the pressure in the left atrium is higher than the pressure in the relaxed left ventricle. So blood passively flows with its pressure gradient from the atrium to the ventricle through the open mitral valve. At this point, the pressure in the aorta is higher than the low pressure in the relaxed left ventricle, so the aortic valve is shut. Also note there's no valve separating these pulmonary veins from the left atrium. This means that blood is actually always flowing back into the atrium at all points in the cardiac cycle. Then there's a spontaneous wave of depolarization sent out from the SA node in the right atrium. That wave of depolarization makes its way through the atrium, causing it to contract and causing an increase in pressure inside the atrium. This causes a little more blood to be actively pumped into the ventricle through that open mitral valve. Contraction of the atrium contributes a relatively small amount of blood to the ventricle, and it isn't required for ventricular filling. But this step becomes much more important at increased heart rates, like during exercise. Next, the wave of depolarization reaches the AV node and then spreads through the ventricular muscle. In response, the ventricular muscle starts to contract, causing the pressure inside the ventricle to rise very quickly. When the pressure in the ventricle becomes greater than the pressure in the atrium, the mitral valve shuts and blood stops flowing from the atrium to the ventricle. The ventricle continues to contract, but at this point, the pressure in the aorta is still greater than the pressure in the ventricle, so the aortic valve remains closed. This period is called isovolumetric contraction because the ventricle is contracting against closed valves. So although the pressure inside the ventricle rises quickly, the volume stays the same. The ventricle continues to contract, and when the pressure in the ventricle finally exceeds the pressure in the aorta, the aortic valve opens, allowing blood to flow down its pressure gradient out of the ventricle and into the aorta, out into the systemic circulation. This process is known as ejection. Together, isovolumetric contraction and ejection make up the part of the cardiac cycle known as ventricular systole, because during this time the ventricle is contracting. Eventually, ventricular repolarization occurs, and as the ventricles relax, the ventricular pressure decreases below the aortic pressure, causing the aortic valve to close. The mitral valve remains closed as well because the pressure in the ventricle is still higher than the pressure in the atrium. This period is called isovolumetric relaxation because the ventricle is relaxing with all the valves closed. During this time, the pressure in the ventricle is quickly dropping, but the volume of blood in the ventricle stays the same. Then we come back to ventricular filling when the pressure in the atrium rises above the pressure in the ventricle, opening that mitral valve, allowing blood to flow down its pressure gradient and fill that left ventricle. The Whitters diagram represents all the events happening during one beat of the heart and shows how they align according to time. At the top, there's the ECG, or the waves of depolarization and repolarization of the cardiac muscle. Next are the pressure waves for the left heart, including the ventricular pressure wave, the aortic pressure wave, and the much lower atrial pressure wave. Opening and closing of the mitral valve and the aortic valve are also indicated on this portion of the diagram because these events depend on changes in pressure. Next are the heart sounds and where they correlate to the cardiac cycle. Then the left ventricular volume over time, showing how this volume changes throughout the beat of the heart. Next is the venous pulse, so this is the pressure wave of the large veins. Finally, there are pressures of the right heart, including the right ventricular, pulmonary artery, and right atrial pressure waves.